In this video, we're going to review basic skills that you should have covered already in previous classes, but we're going to give you a quick refresher here. So starting off with significant digits, essentially significant digits are the digits that are a result of reading the measuring instrument. So not all digits in a measurement are significant. And it's important to know the conventions for sigdigs or significant digits since it's a key skill, especially when doing math or any calculation in chemistry here. Okay, so there are some rules for significant digits, and you could go through these ones, but I'll give you an alternative way that I like talking about sigdigs. So number one is that any digit that is not 0 counts as a significant digit. Yep. Okay, now zeros are going to be a special case here. So you can break the zeros apart into 3 categories: leading zeros, sandwich zeros, and trailing zeros. So leading zeros, which are zeros that come before any digit that is not 0, those are going to be insignificant. So, for example, if we had 0.002, okay, so these zeros right here, they come before the digit that is not 0. Therefore, that's what I mean by leading zeros. Okay, so these are not significant. However, the 2 is because it's a digit that isn't 0. Okay, so this has 1 significant digit to it. Okay, the second case, the sandwich zeros. Those are going to be significant. So, for example, if we have 101, okay, the 1s are significant because they are digits that are not 0. And the 0 in between them, that's what I call a sandwich zero. So a sandwich zero is just a 0 between digits, 2 digits that are not 0. Okay, so all 3 of them are significant. Therefore, this has 3 significant digits. Last but not least, trailing zeros. Those are going to be significant. So, for example, if we have 0.1000, okay, so the 1, it's a non-zero digit, so it's significant. And then these are what I mean by trailing zeros. So they're the zeros that come after a digit that is not 0. Okay, so these are all significant. Therefore, this has 4 sigdigs. Why does it have 4 sigdigs and not 5? Because this first 0 is a leading 0 because it comes before the digit that is not 0, the 1. Okay, so this is a leading 0 right here, so it doesn't count as significant, but everything else is significant. That's why this value has 4 significant digits. Okay, so let's move on to some more examples. Okay, so with 45.81, all of those digits are non-zero digits, therefore all of them are significant, so 4 sigdigs. Okay, with the next one here, the first 3 zeros, those are leading zeros, so they don't count. But the 5 and the 2 count because they're non-zero digits, and then the last 0 is a trailing 0, so it counts. So this has 3 sigdigs. With this next example, the 5 and the 2 count, and then these are all trailing zeros because they come after the non-zero digits. So all of these count, so that is 5 significant digits. Okay, and then we've got some sandwich zeros happening in the last example. So the 1, the 5, and the 2 count, and the sandwich zeros count as well. So that is 2, 4, 6 sigdigs. All right, so not all quantities used in science are a result of measurement, and any quantities based on counting or definition are considered to be perfect numbers. Okay, therefore, counting numbers and definitions, they're going to have infinite amount of sigdigs and no uncertainty exists. Okay, so what does this mean for you? Okay, so essentially, if you have your unit as a word, then you have infinite amount of sigdigs. So if you have a unit as a word, infinite sigdigs. Now the reason being is because, yes, this could be 7 tennis balls, or it could be 7.0 tennis balls, which would be 2 sigdigs, right, because that's a trailing zero and it does count. Or it could be 7.00, so that'd be 3 sigdigs. Or it could be 7.000 tennis balls, or 7.0000000. I don't know how many zeros those are, but many zeros. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So the amount of sigdigs could go on forever and ever and ever because the unit is a word. Okay. So I'm going to do a couple of these examples here just for some more sigdigs examples. So with this first one here, we got 2 leading zeros, they don't count, but the 5 and the 3, they're non-zero digits, therefore they do count, so that's 2 sigdigs. With this next one, all of them count, so 3 sigdigs. Okay, we got some trailing zeros, those count, so this is also 3 sigdigs. We got sandwich zeros, those count, so all of these count, so that's 4 sigdigs. The leading zeros do not count, so we have 3 sigdigs. And then with this one, we've got 2 sigdigs. Okay. Now for number 10, because it has our unit as a word, this would be infinite amount of sigdigs. Okay, moving on to rounding rules. Okay, so rounding rules is just us figuring out if our number, or how we should be rounding our number so that we can get it in the proper amount of sigdigs. Okay, so first thing we're going to want to do is we're going to look at the first digit after those that we need to satisfy sigdigs, and if the number is less than 5, the digits stay the same. However, if it's 5 or greater, then the last digit needs to be bumped up by 1. So, for example, let's say we have the number 2.55, and let's say we want to get it into 2 sigdigs. So what I like to do is I like to count my sigdigs, so 1, 2, so there's my cutoff line. Okay, so now I need to look at the digit after the cutoff line to tell me if I should round the digit just before the cutoff line up or leave it the same. So since this digit is 5, that means we need to round this one just before the cutoff line up by 1. Okay, so that's going to be 2.6. But let's say the number was 2.54. We still wanted to round it off to 2 sigdigs there. Then because this digit right after the cutoff line is less than 5, that means this number or digit right before the cutoff line stays the same. Alright, so let's have a few more examples as to what this looks like. So for the first one, 1.93 rounded to 2 sig digs. So there's my cutoff line. This is lower than 5, therefore rounded off, it would be 1.9 grams. Now to 3 sig digs, so remember leading zeros do not count. So 1, 2, 3. So my cutoff line is right there. 5 is right after the cutoff line, so that means that rounds up this 9. But because the 9 rounds up to 10, that's also going to bump up the next one. So this is going to turn into 0.0051, and we got to put a 0 there because it wants 3 sig digs, and this trailing 0 does count as a sig dig. Okay, and then number 3, round off to 3 sig digs, so I count 1, 2, 3. There's my cutoff line. So the number after the cutoff line is lower than 5, therefore the 6 is going to stay the same, so 39.6. Okay. Now, moving on to scientific notation. So essentially what scientific notation is a way to represent either really big numbers or really small numbers. Okay, and the basic template for scientific notation is you have whatever number. Okay, and you know what, I'm going to specify the template a little bit more. So you only have one digit to the left of the decimal, and then you have however many digits you need to satisfy sig digs, and then times 10 to some exponent. Okay, now with this exponent, there's a couple of things we need to know. So the exponent will be positive. If your original number is bigger than 1. However, the exponent will be negative if your number is between 0 and 1. So it's 0.0 something something. So exponent is negative if original number is between 0 and 1. Okay, so for our example here, we have 4.85 times 10 to the power of 3. So if we wrote that out as, like, when I say original number, I mean the non-scientific notation number. So original, this is scientific notation. Okay, so notice that there's only one digit to the left of the decimal. If you have any more than one digit to the left of the decimal, you are not properly reporting scientific notation. Okay, so looking at this number, we know that this value is going to be bigger than 1 because our exponent is positive. And what the exponent represents is how many times you move the decimal. So because it's 3, and because it's positive, that means I need, like, in order to convert from scientific notation to the original number, I need to take this decimal and move it so that the number gets bigger than 1. So because the exponent is 3, I'm going to move it 3 times to the right. So 1, 2, 3, which is how they're getting 48,000, or sorry, not 48,000, 4,850. Okay. And I'll put in the units there. All right. So for the next couple examples, we're going to be expressing these original numbers in scientific notation, and we're going to round to the sig digs put in the brackets. Okay. So looking at this number, we want to make it so that there's only one non-zero digit to the left of the decimal. So I need to move this decimal 1, 2, 3 over to the right. So then that's 7.35. And then I got to write that times 10 to the power of. Now, since our original number is between 0 and 1, that means my exponent is going to be negative. and I'm going to count how many times I move the decimal. 1, 2, 3. So it's going to be -3. Okay, now we're going to worry about the significant digits. So because it's 2 significant digits, I'm going to count 1, 2. My cutoff line is right there. So this 5 is going to cause the 3 to bump up. So then my final answer here is going to be 7.4 times 10 to the power of -3, and let's not forget units, milliliters. There we go. Let's put a box around my answer. Okay, moving on to the next one here, same process. Okay, so we want to represent this number in scientific notation, so I only want one digit that's not 0 to the left of the decimal, so 1, 2, 3. So 1.3526. I moved the decimal over 3, and since my original number was bigger than 1, it's going to be a +3. Now, we want it in 2 significant digits, so my cutoff line, if I start counting from the far left, is 1, 2. Okay, so the number right after the cutoff line is 5. That means it bumps up the number in front of it. So this is going to be 1.4 times 10 to the power of 3, and our units are kilograms. And there's my answer. All right, for the next example, we're starting with scientific notation, and we're expressing these numbers in long form, or sometimes I call it original form. Okay, so the exponent is negative here. That means my number is between 0 and 1. So that means I'm going to be moving my decimal over to the left 2 spots. So 1, 2, and then I just fill the space with a 0. So if I rate this 0.015. Okay, and we're not asked for a specific amount of sig digs, so I'm not going to worry about that. I'm just going to put in units. Okay, moving on to the next one. Okay, 2.873 times 10 to the power of +3. So the exponent is positive. That means my number is bigger than 1. So I'm moving my decimal over to the right 3 spots. 1, 2, 3. So then my original number is 2,873 kilograms. Okay. Now, for some of these numbers here, they don't have a decimal explicitly written, but what you can do is if there is no decimal written explicitly in the number, it's just going to show up at the very end of the number. Okay. Now, when we are adding or subtracting and multiplying or dividing, special sig dig rules get applied to both cases. So for addition and subtraction, as well as multiplication and division, we need to make sure that we are reporting our answer to the number that has the least amount of significant digits. Okay, so for addition or subtraction, how you figure out how many digits should be in your answer, you're going to look at the digits after the decimal. Okay, and we're going to be going to the least amount of digits after the decimal place. Okay, we also got to make sure whenever you add or subtract that your units are going to be the same. So let's look at this example here. So if we add 2.87 with 1.3, we're going to get 4.17. Okay, now looking at our values that we were given in our question here, we need to go with the significant digits of the number with the least amount of significant digits after the decimal. Okay, so that would be the 1.3. There's only one digit after the decimal, so that means that my answer only needs to have one digit after the decimal. So that means my cutoff line is right here. Okay, now the reason why we're doing it this way is because our answer has to have the same precision as the least precise measurement, which is this 1.3. Okay, so that means my answer should be 4.2, and then I'm going to include units, meters. Okay. If I look at subtraction here, so 3.7 minus 0.18, that's going to give us 3.52. Okay, now again, we're going with the least precise measurement, or in other words, the number that has the least amount of digits after the decimal, which is 3.7, so our cutoff line is right here. So that means that this is going to be 3.5 grams. Okay. Let's do a couple more examples here. I wanted to do one of each first, like one of adding, one of subtracting first before I moved on. Okay. With this example here, since both of these values have just one digit after the decimal, like it's pretty clear that our answer should just have one digit after the decimal. So if we add these, we get 3.2 seconds, and that's in the proper amount of sigdigs. Okay. But looking at this, so one of these has 3 digits after the decimal, the other one has 2. We're going to go with the value that has just 2 digits after the decimal, and so our final answer is going to have only 2 digits after the decimal. So that's going to be 3.567, and then 2 digits after the decimal. Our cutoff line is right there, so that we get 3.57. Okay. Moving on to multiplication and division. Essentially, what you're going to do is, in order to figure out sigdigs, you're going to look at the whole number for all of the numbers that you're given and just count up which number has the least amount of sigdigs in total. Not just after the decimal point, but in total. So look at the whole number for multiplication and division. Okay, and your answer is going to have the same number of sigdigs as your number with the least amount of sigdigs. Okay, so example number 1, we got 2.55 kilojoules per mole times 3.4, so that's going to give us 8.67. Now, if I take a look at my sigdigs, so this value here, the 2.55, that has 3 sigdigs, because 1, 2, 3, and then my other number has 2 sigdigs. So I'm going to go with the one with the least amount of sigdigs, so that means my answer has to have 2 sigdigs. So I'm going to draw my cutoff line after first 2 sigdigs, and then my answer will be 8.7. Now, what's going to happen with the units here? So if you wanted to do something called unit analysis, so I'm just going to write the units, I'm not going to worry about the numbers. So we got kilojoules per mole, and we multiplied it by mole. So unit analysis basically just says if you have the exact same thing on the top and the bottom, they're going to cancel out. Notice how we have the exact same thing in the numerator and denominator. That means they cancel out. So that means our units are kilojoules. So this is 8.7 kilojoules. Okay, let's do the same sort of idea with the next one. So we have 100 centimeters per second times by 4.000 seconds. Okay, so I'm just writing this out so I can show you how the unit analysis works. But looking at our numbers, so the first number, 100 centimeters per second, it has 1, 2, 3 sigdigs. Okay, the next one has 1, 2, 3, 4 sigdigs. We always go with the one with the least amount of sigdigs. So our final answer is going to have 3 sigdigs in it. So 100 times 4, that's going to give us 400. Now, what are our units? Well, we have seconds in the denominator, seconds in the numerator. Therefore, seconds cancels out. What are we left with? Centimeters. So this is going to be 400 centimeters. And it's already in 3 sigdigs here. Okay, now with division, same sort of idea. Okay, so we have 1, 2, 3 sigdigs here, 1, 2 sigdigs there. So we're going 75.3 moles, and we're dividing it by 3 liters. So once we divide that out, that's going to give us 25.1. Okay, now looking at this here, we got to go with 2 sigdigs for our final answer. So that means my cutoff line is right on the decimal. So 25, and with our units here, we didn't have the same thing on the numerator and denominator, so nothing cancels out. So the units are going to be moles per liter. Okay. All right, so this section is just talking about it. It'll eventually lead to more discussion about unit analysis, which you can use to help you do calculations throughout a large portion of this course. So I'll just do it fairly quickly here. So when we're multiplying fractions here, like comparing this to unit analysis, notice how we have the same number in the numerator and denominator. Right? So you can cancel those out and we'll get 1/4. Okay? If you wanted to just like prove to yourself that like this works, right, you could just multiply this fraction normally and then simplify it. But if we did that, so 3/4 times 1/3, so we would multiply numerator with numerator, so that'd be 3, and then denominator with denominator, that'd be 12. We can simplify this by dividing both the top and the bottom by 3, not 4, which would still give us 1/4. Okay. Now, with dividing fractions, as a quick refresher, how you divide fractions is you flip the fraction that comes second and then you change the divide sign into a multiply sign. So doing that, we would have 1/7 multiplied by 7/17. So notice how we have 7 in the denominator and numerator. Those cancel out. So we get 1/17 for our answer. Okay, so that's just a quick refresher of like how canceling out works when we're dealing with fractions, which can help us understand why we cancel out units the way we do in unit analysis. So moving on to another example where we're multiplying fractions, but now units are involved. So notice how we have hours in the numerator and denominator. Those cancel out. And so our answer will be 15 kilometers there. Right now I'm not worried about sigdigs. The whole point of this is to take a break from sigdigs so I can illustrate the point of how unit analysis works. Okay. If I did this other example of how many kilometers have you traveled in 8 hours at 110 kilometers per hour, well, with this one here, if we're trying to find kilometers and we're given 110 kilometers per hour, right, and we're trying to figure out, okay, how many kilometers did we travel? Well, I know I want to cancel out the hours, and since hours is on the bottom, I just need to put hours on top. We were given a time, 8 hours, so the hours, those cancel out. 110 multiplied by 8 is going to be 880 kilometers. Okay, so that's just a quick example, or a couple of quick examples as to how unit analysis works. If you have the exact same unit in the numerator as well as the denominator, they are going to cancel out. Okay, another reminder from earlier science classes here is metric conversions. Okay, so with metric conversions, how I like to make it easy for myself to convert is I like to use this metric conversion. I call it a metric conversion line. So I'll write it out first, and then I'll give you the mnemonic or the memory device that I use in order to memorize this entire thing, because it gets a little bit lengthy. Okay, so what all of these letters mean are just like the prefixes. So T is for tera, G is for giga, M is for mega, kilo, hecta, deca. Base units are just any units where it obviously doesn't have a prefix there. Most of the time, base units, they're represented just by one letter as an abbreviation. So for example, meters, liters, grams. But there are exceptions to that, like base units in chemistry could be moles. So just heads up on that. D stands for deci, centi, milli, micro, nano, pico. And now these spaces in between some of these prefixes, they're just placeholders to help you count so that you can properly convert between metric units. Okay, so how I remember this entire metric conversion line is starting at the T. The girl's mother killed her dad, and then there's nothing for the base units. Death can make you not pretty. So a little bit morbid, I know, but I have remembered it ever since the first day that was taught to me, so it works pretty well. Okay, all right, so let's figure out how do we actually use this metric conversion line. Okay, so looking at this first question, we're not worried about sigdigs, we're just worried about, okay, how do we convert between units? So we're going from milligrams to grams. So how I'd do it is I'd be like, okay, where is milligrams on this line? So milligrams is going to be right here. Now, tricky thing about the M's is that little m right there stands for milli. Big M stands for mega. Do not get it confused with M for meters, which is a base unit. Okay, so just watch out for that. anyways, we're starting at milligrams and we want to go to grams, which is a base unit. Okay, so I kind of map up where I'm starting, where I want to go, and then I start where with the units I'm given, and then I count 1, 2, 3. So this tells me that I need to move the decimal 3 to the left. So 1, 2, 3. So 2,000 milligrams is equivalent to 2 grams. Okay, I'm not going to worry about sig digs. The whole point of this is to just figure out how the metric conversion line works. Okay, for the next one, we're going from 104 kilometers to meters. So kilometers, kilo is right there. Meters, right here. So I start at kilometers, 1, 2, 3. So that means I move the decimal 3 to the right. Whenever the decimal isn't written, it's assumed that it's at the end of the number. So 1, 2, 3, and then I fill in these placeholders with zeros. So I'm going to write it in the space here. So 104 kilometers is equivalent to 104,000 meters. With the next one here, we have 4.8 megagrams. So mega is right here, and then grams is right here. So I'm going to count, and I need to count these placeholders when I move my pencil over. So 1, 2, 3, 4, 5, 6. So I got to move the decimal 6 to the right. So 1, 2, actually hang on one second. 1, 2, 3, 4, 5, 6. So we have 48, and then what? That's 1, 2, 3, 4, 5 zeros after it. So 48. There we go. So what is that? That's going to be 4,800,000 grams, I should say. Okay, so with all of these, it's going to be the same technique. You figure out where you're starting, you figure out where you need to get to, and then you count how many spots and in what direction you need to go on the metric conversion line in order to get to where you want to go. Okay. Now, with this next example, they're just asking you to compare the numbers. So what's bigger, what's smaller, or are they equivalent? So for example, if I was looking at 63 millimeters compared to 6 meters, right, obviously 6 meters is going to be the bigger of the two. So with this, I would say that if you want to pretend that this inequality sign is like an alligator, the alligator always eats the bigger of the two numbers. So 6 meters is bigger than 63 millimeters. Okay. So that's just a quick example, but if it helps, you can use the metric conversion line. If you're really having trouble, I would recommend like converting both numbers to the same units, whichever units you want, in order to help you figure out what's bigger, what's smaller, or if they're equivalent values here. So like, for example, where'd it go? Between 1,500 milliliters and 1.5 liters, well, if I converted the milliliters to liters, just because I'm having a hard time figuring out if one's bigger or less than or equivalent, right? Milliliters is here, liters is there. So 1, 2, 3 to the left. So 1, 2, 3 to the left. This is 1.5 liters. So these values are actually equivalent.